Year 10 Maths, 10.2.5, Proving Similar Triangles. We've already looked at similar figures and that they're just really an enlargement. One is an enlargement of the other, or one's a reduction of the other, whichever way you want to think of them. So sides are in the same proportion and angles remain the same. Now we're going to look specifically at triangles. They're very useful. There's a lot of things we can do with them, and we're going to take a look at a few examples. First thing we've got to do, though, is just go through and check we can see all of the tests for similarity. Obviously, if the sides are in the same proportion, then we will have similar figures. We've already looked at that. That's true for all figures, including triangles. Similarly, if we have two sides in proportion and the angle in between them being equal, so you can see here 1 and 2, 2 and 4, so the one on the right is double the one on the left, the angle in between is the same, then that remaining side would be in proportion in each of the triangles. The third one, this is the first one that's different to the congruence tests. 3 corresponding angles are equal. This will guarantee that your triangles are similar. If they have all the same angles, they will be similar. This is also true for all squares. If I take any square, all the angles are equal there, and if I take a larger square, I can easily get that by multiplying by a constant, a scale factor. So that works. What it doesn't work for is rectangles. They may have the same angles. There's an example of a rectangle, but clearly that's not similar to either of the squares, or indeed that square that I'm taking, having a lot of fun drawing all those extra markers on. They're not similar. But with triangles, the angles are equal, the triangles will be similar. Finally, you've got the RHS, right angle hypotenuse, and one other side. If you have that with sides in proportion instead of being equal this time, you don't have congruence, you have similarity. Let's have a look at some really quick examples. This is out of the sort of fluency section, so pretty straightforward. Prove that the following pairs of triangles are similar. Well, 70 and 65, 70 and 65. Given that all triangles have 180 degrees, those two angles must be equal. So I have angle, angle, angle being the reason why triangle ABC is similar to triangle DEF. This time here I've got sides of 1 and 3 with an angle of 120, 2 and 6 with an angle of 120 in between. So that's a side, angle, side in proportion. That would be why those two triangles are similar. Part C, clearly we've got a right angle, we've got a hypotenuse in proportion, it's been doubled, and the other side is in proportion. 4 went to 8. Notice that's the longer side from the right angle. Yep, that works. So that's the right angle, hypotenuse, and side rule. And finally, if we look at the shortest side, 4. If I multiply it by 4, I get 16. 7 times 4 is 28. 8 by 4 is 32. So that's a side, side, side rule. All sides are in proportion. Those triangles will be similar. That's a bit easy. Let's have a look at a couple of the harder or more challenging examples. First one here we're going to have a look at is D. Now, the first trick you've got to do is figure out what triangles are they even talking about. If you're not sure, let's just start by marking things we know. This angle here, between the 5 and the 8, must be the same as that angle between side length B and 24, because they are alternate angles. Some of you would call it your Z rule. I would call them alternate angles. Let's have a look at the other one. On the other side, oh, there's an A. Ooh, that was interesting. That angle there, apologies if you're red-green colourblind, I didn't really think that through, did I? They'll look like different shades anyway. There we have another Z rule, so those two angles are equal. And we also have a pair of vertically opposite angles there. If my pen is going to... No, it doesn't want to work at all. Oh, well, I'll persevere in green, that's a little bit annoying. Not to worry, that angle there. Now it's just going to erase everything. Let's pause and I'll see if I can fix it, and then I'll keep going. Back in business, it didn't actually take me too long. Don't know what was going on. Oh, it still wants to play up a little bit, but we'll get it to work. This angle there, vertically opposite the other angle there. So I do have corresponding sides, but it's important you get the corresponding sides together. Obviously the parallel sides correspond to each other. That's not too bad. Now this side A is between the green angle and the dot, so that's got to correspond to 12, and that leaves the other two sides that are corresponding, being the 5 and the B. So how do I figure out what A and B are? Well, first of all, let's figure out the scale factor. I went from 8 to 24. Now you can use the scale factor equals the second one divided by the first one. I'm just going to do that. 24 divided by 8 equals 3. Of course, you can just see that you multiplied by 3 to go from the smaller one to the large one. Either way is fine. If that's the case, A times 3 would equal 12. A is going to equal 4. And 5 times 3 is going to equal B. B equals 15. Not too bad. One of the clever uses of similar triangles, and this is really clever, both these demonstrations or examples here in question 11. Aaron and Jenny are trying to measure the width of a river. They notice a tree on the opposite bank and they decide to place rocks. You can see the little dots where they've placed rocks. That's just to give them little marker points. And they're going to use that and their knowledge of similar triangles to calculate the width of the river. Have they constructed a pair of similar triangles? Well, let's check it out. This angle must be the same in each of both the large triangle and the smaller triangle for Aaron. They've got a right angle, which would mean the third side is the same. So yes, they're going to be the same. Angle, angle, angle. What about Jenny's? Well, vertically opposite angles are equal, so that's okay. Oh, she's made these lines parallel at a right angle, so the other angle must also be equal. Yep, so once again, Jenny has made similar triangles using angle, angle, angle. We can tick off part A. Then it says use Jenny's first to calculate the width. Alright, well, when I do these, I like to spin my triangles around so they're oriented in the same way. So it's a short side of 8, longer side of 10, and we don't know how long the hypotenuse is. It's now oriented the same as a larger triangle, which has a W there that I'm trying to figure out, and 25 there. Number of ways you can do it. You can use ratios. W over 25 equals 8 over 10. I could even do W divided by 8 equals 25 divided by 10. That would be the same. But for this one, I'm just going to go, look at that scale factor. It's 2.5. So W is going to equal 8 by 2.5. W equals 20. And this is in meters. So that's not too bad. What about if I use Aaron's triangles? Let's have a look at what his triangles are. If I've got two triangles there, I would still draw them separately. It just makes your life a little bit easier. This is W plus 5. You can see the full length is the width plus another 5 meters, so W plus 5. That plus doesn't really look like a plus. Have I mentioned how much I enjoy these new computers we've been provided with? You can see now it's not working again. I will pause until I get it working. Hang on a tick. Well, you didn't have to hang on too long. It didn't take me too much longer, but it took a little bit. So the large triangle, W plus 5, is the long side, and the long vertical side, and there's 15, the shorter of the two legs on which the hypotenuse is built. And if I look at the smaller triangle, which just covers the width of the river, this is a W, and that's a 12. Now, I think I'm going to make sure when I construct these ratios, I keep my W's on top. I could notice that I'm multiplying by 4/5 or by 4/3, depending on which way we're going. But let's not do that. Let's actually do the ratios this time. So I've got W plus 5 divided by 15 equals W over 12. The sides will be in proportion, so that ratio should stay the same. We don't like that denominator, so we're going to multiply by a common denominator. 15 and 12 both go into 60, so let's multiply by that. So you remember this from our very first week, how we get rid of those denominators and make our lives easier. So I'm going to multiply the left-hand one by 16. 15 will go into 64 times, so I'll be left with 4W, and 4 5s are 20. And on the right-hand side, 12 goes into it 5 times, so 4W plus 20 equals 5W. If I subtract 4W from each side, I get 20 equals W. That's in meters. So they both work. Which pair of triangles did you prefer to use? Well, either are good, but I reckon Jenny's made the calculation a little bit more obvious and a little bit easier. You may have found it different. Either way, I hope it helps. A bit of a longer video, that one, but that'll do for now. There's some good problem solving in there. Have a good go, and we'll see you in the next video.